Hello everyone, welcome to today's webinar on balanced cantilever bridge analysis and design using IRC112 2011. So these are the things through which we'll go today. First of all, I'll just discuss today's objective of the webinar. Then we'll have a look at the new release feature for specific India region in concrete design. Then the specifications for the bridge which we will be covering today, and finally the modeling for the same. So this is what we will do today. First of all, we'll use the FCM wizard for initial modeling. We'll modify that later for creating the substructure. Then we'll define the time dependent material properties and we'll link it to the respective material. Then the moving loads for the curved bridges, how those can be defined. Then the uniform temperature and temperature gradient load applications for these curved PSC sections. Then how to apply pressure load on line element. Now this is what we'll be specifically using for the wind load application on the box girder. Then the PSC wizard usage for providing reinforcement. Like when we talk about balanced cantilever bridge, it has sections with curved profile. So providing reinforcement in each and every section manually would be quite cumbersome. So we have a wizard for that as well. That would be the PSC wizard, and we'll see how that could be used for reinforcement application. Then we'll apply the settlement and the required boundary change assignment with that. And finally, we'll perform the PSC design for the box and RC design for the pier or the pile. Okay, so the new design features which have been released for India. So first of all, the PSC design, this has been released last year. So initially you just give the parameters in accordance to codal guidelines, and there are even certain additional parameters which are kept in light that maybe like how Indian codes usually do get updated. So if they are updated and the parameters are modified, then user could manually modify the parameters as well. So you modify the parameters first, then you perform the design. So once the design is performed, you get a detailed Excel report wherein the different steps that have been used, as you could notice over here, how the neutral axis depth has been calculated. Okay, so these kind of detailed steps would be available. All the design considerations, the material properties, the areas and everything, all the factors used would be mentioned in this report. Moreover, the clause which has been used for a particular calculation as well as its formulae and whether it is passing or whether it is not good would also be mentioned in the report. So these reports are so detailed that you could literally just, once it is ready, you could simply take a print of it and submit it to the clients. Then the new thing which is added is the composite section design. So earlier, if you might have noticed on performing the design, the dialog box would appear wherein you just have to enter, you modify the material, you just have to enter the reinforcement for the specified material. But now, if you have created a model with composite general sections, then when you want to modify the material under the design tab, at that time, this kind of a bigger dialog box will appear wherein separate concrete and rebar properties for girder as well as slab would be asked. Okay, and next one is finally the RC design. So RC design based on IRC112 is available now for beams as well as columns. Now coming to today's project. So when we talk about a balanced cantilever bridge, the things that an engineer need to consider are camber, because during the construction there will be deformations, and at the end when you are joining the finally balanced segments of the bridges, there would be certain deformations which may cause defects. So the camber needs to be considered by the engineer. Then obviously the pre-stress loss, creep and shrinkage, as well as the construction sequences to when which segments are cast and when is the final key segment cast. These things need to be properly considered. There have been webinars earlier in which we have covered camber quite in detail. So for today, what we will be focusing on is different modeling techniques which are not generally covered, as well as use of PSC wizard, and finally a bit on IRC design. Okay, so this is the cross section. The webs are 350 mm thick. The total height of the section at the pier location is about 6 meters. And at the mid, the total height is about 2.6 meters. This is the overall geometry. The radius of curvature for the balanced cantilever bridge is 500 meter, and the total curved length is 290 meter, in which the first span is of 80 meter, second span is of 120 meter, and the third span is of 90 meters. Okay, so these are the data which have been considered. So obviously material design code is IRC112, moving load is IRC6. The concrete material for box girder is M50. For pier and pier cap it's M40, and for pile and pile cap it's M30. The reinforcement grade considered overall is Fe415. Pre-stressing tendons have been kept as 19-15 for simplicity. The soil separate reaction is assumed as 25,000 kilonewton per cubic meter. We are assuming this because obviously we will be providing the soil springs for the piles in the model. The crash barrier load is assumed as 12.5 kilonewton per meter, and wearing force load is taken as 21.34 kilonewton per meter. These calculations are quite simple. Now the moving load. In this case, the width of the deck has been taken as just 9.7 meter. Reason being, that restricts us to 2 lanes, and we don't need to keep on defining more moving load lanes, as that is clear. Okay, so since we have taken width of deck as 9.7 and 0.5 on either side is taken up by the crash barrier, so the carriage width would be 8.7 meter. Hence, we will be considering the 2 lanes. So 2 lanes of class A and 1 lane of class 70R are the cases which should be checked. So vehicles considered are class A and 70R. These are the eccentricity calculations. The eccentricity for class A lane 1, lane 2, and then the eccentricity for class 70R lane. Then the braking loads have been approximately calculated based on IRC6, that is the 20% load for the first train and 10% for the following trains for the different spans, and accordingly whatever load is coming on each and every support location would be directly applied at those nodes 1.2 meter above the deck. Okay, so these are the loads which are calculated for that. The braking load on left support is about 13.9 tons. On pier 1 is 32.25 ton. Pier 2 is 33.35, and right support it is about 15 ton. Now this depends on the span length, that is quite clear. Wind load. So the pressure considered in this case is 0.551 kilonewton per meter square. Gust factor is taken as 2, drag coefficient as 1.5. So the design pressure which we are going to consider is 1.653 kilonewton per meter square. And the height of crash barrier above superstructure, it is assumed as 1.5 meter. Okay, in this case, live load on wind load on live load is ignored. Okay, and these are the reinforcement detail. For longitudinal direction, we would be considering 16 mm dia bars spaced at 150 meter center to center. So that gives us 64 bars at the top, and the bars in the web to resist the torsion, those are considered to be 25. Whereas for shear, we are considering 12 mm bar with a spacing of 150 mm in longitudinal direction and total 6 number of legs. Basically, the box that we are considering is a twin cell, so 6 legs for the stirrups are considered. Okay, so moving on, we'll just switch to live modeling. Okay, so we all know how to define the material properties and section properties, so I'll skip that and I'll just come to the balanced cantilever bridge modeling. So we go to FCM bridge wizard. Okay, I'll just open a wizard and explain the value inputs. Okay, so here when you import a wizard, so basically that's nothing but a text file which you have made earlier, which could be taken up to enter the values over here. As you can notice, when we see the material, that is girder and pier 1 and 2, these are the text input which were there. Okay, so those have directly come, but the material have not been defined in accordance to that. So we'll have to define these materials. So I'll just click on these 3 dots beside material, so that will take me to material properties dialog box. And rather than adding all the materials, I'll simply import these. So I'll go to import. Okay, so these are the materials which will be taken up for box, pier, pile and tendon. Okay, so the 4 materials have come up. As you can notice, the works tree is also updated. Okay, so now the appropriate material is coming up over here. Similarly, when we come to section side, the number is there, but the section itself is missing. So we'll import the required section. Import. Okay, and we just want to import pier, pile cap and pile sections. So I'll just import those. Remaining will be generating. Rather, the wizard would be doing it for us. Okay. Okay, so all the required material and the sections have been imported. Now coming to the wizard dialog box. So basically these are quite simple to explain. So the material you have to enter for girder for your pier. Similarly, what section of pier you are taking. Then what is the stage duration? So here it is assumed as 10 days. So for each and every segment addition, 10 days time would be taken up. The total number of piers considered is 2. Method is cast in. So the segments are actually cast at the location. They are not precast and put in place. If they are precast, you have to select here PSM, precast segment method. Okay. We are considering our bridge to be curved. So the radius is 500 meters and it's convex curve. Now the pier table placement. So what is pier table basically? This could be noticed from the guide diagram. Okay, PT basically means this part, that is pier table, and B is the constant depth part of the pier table. Okay, so in this case I have selected the advanced. Now why I have done that is because I have given this as a double diaphragm. Okay, so there is a curved portion which is coming, then there's a diaphragm at one location, then in mid part again it is hollow. Okay, because there is not much shear there. Then again there's a diaphragm near the pier location and then it starts receding. So this double kind of profile was defined, and accordingly the input of T1, T2, T3 and means all these required input based on the guide diagram have been made. Okay, so the pier table advanced placement is taken up. Then the key segment, that is K1 and K2, that is key segment between FSM fully supported part and the balanced cantilever part, as well as the key segment between 2 different balanced cantilever part is 1 meter in length. The pier height is taken as 20 meters and C is 0. C means if say at certain location there are instead of a single huge pier there are 2 piers. So in that case you have to enter this C, which is the spacing between the 2 pier locations in the same 2 piers in the same location. Then the FSML and FSMR part. Okay, so these the fully supported part on the left is 20 meter and on the right is 30 meters. Okay, and the segments in zone 1 and zone 2. So actually what does this 27 at 2 means? 27 segments of 2 meter length each are there in zone 1 and zone 2. Okay, so with this, the distance from the center of the pier to the center of the first key segment is 60 meters. Okay, so 27 at 2, that is 54. Say we are considering zone 1, so this is 54, and then half of the pier table length. So pier table is 12 meter in length. Okay, accordingly B also has been input as 12. So 54 plus 6, that is 60 meters. So this is how we could put the input for the model generation. Then the section part. Okay, so here you could select whether it's a 1 cell or a 2 cell box. So in our case it's a 2 cell box. Then you simply have to enter the required dimensions over here. Okay, you could check the guide diagram for that, and you could click on drawing to know the final sections which have been input. Moreover, in this case we are inputting like this because the sections could be generated. If that's a case wherein you can't generate the sections like this, you could just select type 2 and you could select the sections. No doubt you will have to define these. Okay, so I'll just switch to type 1 and this would be used. We are including the wet concrete weight as well as the crane load. Then the tendon. Okay, so we have defined the material, we have defined the sections, but we have not defined the tendon properties yet. So we'll quickly define that. Just click on the 3 dots here, click add, say tendon. Material we are taking as tendon. Total area. Now we are going to use 19T15. So rather than calculating the area manually and entering, you could just click on these 3 dots besides tendon area. So we will select 15 mm dia and 19 numbers and OK. So accordingly the area field would be updated. The diameter, say we are taking 0.12. Relaxation based on IRC112, and remaining properties remain the same. Okay, we'll just save this one. Okay, so we have entered the tendon properties, everything is done. The tendons in the separate parts of the section, they are demarcated over here. If you want to change the number of tendons in different locations, you could just click on this tendon number and you could update in which part how many tendons you want. Okay, here it shows that this N7 and N8, that is N7 and 8 as well as N13 and N14, these are for the FSM part, whereas the remaining are for the balanced cantilever part. Okay, so based on your length of the bridge as well as your number of key segments, the number of tendons would be automatically taken up by the software itself. However, if you want to edit it, you could do that from over there. Okay, and now I'll just click OK. So this will generate my 290 meter span, 500 meter curved balanced cantilever bridge, and with just this much input, as you can notice, total 151 elements have been generated, 31 construction stages have been generated, and we had just defined 3 sections, whether we had imported 3 sections, but now total 8 sections have been created. Now coming to the diaphragm part. Okay, so it's a completely filled up diaphragm. However, if you want to edit the section properties, then you could do that over here to add a manhole from in the solid diaphragm section. Okay, so as you can notice, the self weight, the pre-stress loads, and it's 2 216 pre-stressing tendons. What we have done was we have just defined one tendon property. So 216 tendons have been given by this itself. Coming to the construction stages, now if you want to see, okay, self weight is okay, form work traveler. If we see over here, it seems like it's crazy, right? There are lots of vertical loads and lots of moments acting due to the crane as well as the wet concrete. But if we check in the construction stage, okay, so these loads are activated and deactivated at the required times. Okay. Okay, so this is it. This is how the basic model could be generated. Moving on, the things that are left over here is the time dependent material property definition. So we'll quickly define that. This is also covered in several webinars. So we'll just quickly go through this procedure. For creep and shrinkage, we'll select IRC112, say M50 CNS, 50,000 kilonewton per meter square, notional size of 1 meter. Okay. Similarly for compressive strength, select the code to IRC112, M50 comp. Now here the mean compressive strength is to be entered, that is FCK plus delta F. So for M50 grade of concrete, this would be 60,000 kilonewton per meter square. We're considering normal cement, and at 28 days it is 60,000, so that's okay. And we'll quickly link these. So material link, creep and shrinkage M50, compressive strength M50, and box. Okay, so now I have defined it only for the box girder because, well, creep and shrinkage and those things play a major role in the longitudinal direction rather than the vertical direction. So I'm not defining those for the piers. Okay, so this has been done. Now what we'll do is we'll quickly model the substructure. So I'll just activate piers for now. Okay, so the pier cap is 1.8 meter in thickness. So I'll simply extrude it quickly. We'll go to nodes and elements, extrude. Material is pile, the pile cap. If I said pier cap earlier. Pile cap in Z direction by minus 1.8 meter and apply. Okay, so this is my pile cap basically. Now we'll be creating the piles. So the piles are of 1.2 meter diameter, and hence the spacing in between this is 3.6, that is 3 times the diameter. Okay, so this is 1.2 meter diameter of pile, and my pile caps are 15.9 meter by 15.9 meter. So I'll quickly generate the nodes for the pile location. Okay, so we'll do it simultaneously at both the locations. In this case, we have assumed, as you can see, a square configuration with 5 pipes in each direction. Okay, so I'll go to translate nodes. I want to copy my nodes. Unequal distance, say in X direction. First node I want to generate at minus 7.2, after which 4 at 3.6. Okay, and I say apply. So this is what it does, right? This first node, it was copied first of all at this location, and then 4 times, 1, 2, 3 and 4 times after that location. So these are the relative distance, and here the merge duplicate node option is checked. So obviously the node which was created at the center was a duplicate node, so that has been merged into the existing node. Okay, similarly, so these 5 nodes have been created. We translated them in X. Similarly, what we'll do is now we'll translate these in Y direction. So I'll just change this to Y and apply. Because now if I look in plan, all the nodes for my piles have been created. Okay, and out of these, I'll just simply extrude my piles. So I'll just select all these, extrude, material is pile, section pile, sorry, z direction minus 1 meter, say 30 times, so 30 meter long piles. Okay, and apply. So my piles have been generated. Now for FCM bridge which has been generated using the wizard, the construction stages are already there, right? We want to activate our piles and the pile cap along with the pier in the first construction stage itself. Okay, however, these are not there in any structure group. So as you know, if you want to add something to a construction stage, it has to be in a group. For elements, it has to be in structure group. For loads, it has to be in load group. And for boundaries, it has to be in boundary group. Okay, so we'll just create those groups now. So go to group, new, okay, pile and pile cap 1. Okay, this has come. Similarly, we'll add one more. Pile and pile cap 2. Okay, so in this, what we'll do is we'll just add the nodes below the respective pier. So when we talk about pier 1, so it is this location, right? So all the elements as well as nodes of pile and pile cap would be added up to this group, that is pile and PC 1. Similarly, for the other side, we'll add it to the pile and PC 2 group. Okay. Boundary groups are already there, and we'll need to create one more group for the SIDL. Right now, the load groups which are created are pertaining to pre-stressing as well as the wet concrete load as well as the self-weight, but SIDL is not automatically added by the wizard, so we'll need to create a load group for the SIDL. So I'll just click new and SIDL. Okay. So structure group I have added. Now I'll be adding the boundaries. If I check the support group, support boundary group basically. Okay. So right now it is having these locations in it because there are supports at these locations. Wizard was not considering the structure below the pier. So there are fixed support at this location, but now since we are considering piles and pile cap, we'll have to remove these supports. So I'll just activate the entire structure. Okay, and I'll remove these supports basically. So to do that, I could either do it from the table over here. Okay, so these are the supports at the pier location. I could simply remove it, or I could go. So now basically if we check, I think I'll show the support conditions before I remove it so that it's clear. Okay, so right now this is the support condition. Okay, if I want to remove these supports, so for these support, all the displacement as well as all the rotations are restrained. Okay, so when we check the boundary types, type 1 has everything restrained except the warping, whereas type 2, dx is free, dy, dz and rx is restrained. Hence, dy, dz and rx are green, remaining are black. Okay, what we want to remove are the completely fixed ones, so we have to delete the type 1. Okay, and the supports there are gone. Now what we'll do is we'll add the pile springs. So I'll just zoom in on the pile part again. Okay, so we'll go to boundaries, integral bridge spring. Okay, so when you use this thing, the springs would be assigned to the relevant structural element in accordance to soil stiffness calculation based on BM Lehne. Okay, so we want to provide pile spring for the support boundary group. We are considering this thing as soft clay, say for example. Ground level. The ground level is generally assumed 500 mm above the pile cap, and if we are talking about flyover bridges. So let us just check. This is minus 16.8 meter, right? So I'll just change it to minus 16.3, that is 500 mm above the pile cap. Diameter of piles is 1.2 meter. Unit weight of soil, coefficient of earth pressure, subgrade modules of reaction. Now this is what we had taken as 25,000. So we'll do that. Okay, now we have to select the nodes along the pile. So I'll just click select by window and I'll select all the nodes and elements. Here the element selection doesn't matter, but it is going to happen anyway. So, but the spring coefficient would be assigned to node only, so we don't need to worry about that. So we select the relevant nodes and we say apply. Okay, so here, as you can notice, at each and every location in pile, the vertical restraint in accordance to soil stiffness, as well as display it from here. The multilinear springs have also been assigned. I guess I'll have to show you the properties. Okay, so what are these springs? These springs are basically my pile springs restrained in horizontal and horizontal, that is longitudinal and lateral directions. Okay, so with what displacement, what force would be required. So all of this calculation happens in accordance to the subgrade modules of reaction that we have provided. Okay, but I think we have made certain error in putting this up. This node location coordinate is 0 so far as I know. No, it has to be less. No, that's proper. Okay, so moving on, the springs have been assigned. Now what we'll do is we'll modify the construction stages. The wizard, what it will do is it will generate the construction stages all of 10 days duration. Okay, however, we need to add one more stage, which is going to be your long duration stage. Okay, so we say add in this, we give CS 32 because 31 was already there. Let us say its duration is 9,700 days, so the overall duration will become 10,000 days. Okay, so we'll just do this and okay, this is done. As well as for the stage 1, okay, we created the pile cap and the pile group, but those have not been added over here, so we'll just add those, pile and pile cap, and we'll give this as age 1 because we have not defined any time dependent material property for it. So anyway, it will be taken as the mean strength. Add and okay, close. So now if I check the first construction stage, my pile and pile cap has come. Moreover, even the support conditions have been modified, but since those have been added to the same boundary group, we don't need to edit the boundary groups. Okay, so now what we'll do is now we'll define the different static load cases which we would be considering after the construction stages. So for that we go to load, static load cases, and these are the existing ones. What I'll do is I'll add the remaining. So first of all, for SIDL, now SIDL also I am going to add in my construction stage, so its type should be taken as a construction stage load. Okay, add. Then what we are going to add is the braking load application in this case. So say braking, its type would be taken as longitudinal force from live load. Add. Similarly, we'll be adding the positive and negative uniform temperature cases. Pause unit temp, say temperature. Add. Similarly, negative uniform temperature. Then the positive temperature gradient. type is temperature gradient, add, and similarly negative temperature gradient, and finally the wind. So we are just considering wind load on structure and not on the live load. So wind load on structure, add, and done. So the relevant load cases have now been added. Now simply speaking, we'll just add load to these things. So SIDL, obviously it's going to be applied to my superstructure. So I have just come to the front view. I'll just activate the superstructure, or rather select the superstructure. Okay, so with this, all the superstructure elements are selected. Okay, and I'll go to load, element load. The load case is SIDL. Load group, we have to select SIDL. Okay, and when we talk about varying course load, it would be acting at the center, it won't be having any eccentricity. So simply I have to change this to minus 21.34. This is the value that I had shown in the PPT, and apply. Okay, so my SIDL has been applied for the overall bridge. I have to select the same elements and I have to assign the crash barrier load under the same load case. So what I'll do is I'll just click on this button, which is select previous. So all the elements have been selected again. Now the crash barrier would be eccentric, right? So we have to check this eccentric over here from the offset location, that is the center top, which we have selected. The direction as local y, that is in transverse direction for each element. The eccentricity would be basically 9.7 by 2, right? And the width of the crash barrier is assumed as 0.5 meter. So 9.7 by 2 minus 0.25. So that brings us, or rather we could directly enter it that way over here, 9.7 by 2 minus 0.25. Okay, so we just enter this value in global z direction. This should be minus 12.5 kilonewton per meter, and I say apply. Okay, so I'll just zoom in. Okay, so as you can notice, the software auto calculates even from these kind of input, and you don't need to calculate the value manually elsewhere and put it on. You just enter the formula and it will calculate. Okay, so this has been done once. Similarly for the crash barrier on the other side, I'll just click on this select previous. I'll change this sign to minus, and I'll say apply. Okay, so the crash barrier load has been applied at both the locations. Okay, this is done. Now moving on to the braking load. Okay, so braking load in accordance to clause of IRC6 acts at 1.2 meter above the deck location, plus the major bending moment contribution due to braking load would be happening for the pier, and the impact on deck would be less. So what is taken in this case is the braking load is calculated for one span, and it is equally distributed on either side of the either support of the span. Okay, so that way simply the braking load was calculated. So we'll be applying these to these nodes. However, if we apply braking load to node, we have to rotate the node local axis to give the braking load in the direction of the bridge. To avoid that, what we can do is we could provide this nodal load as element load. Now I'll just show you how to do that. So for that, I'll just select the relevant elements first to avoid confusion. Okay, so what we are going to do is we are going to apply this nodal load on I node of the element. So this is my central element, so I'll select this one because I want to apply load over here, that is the I node. Similarly, this element over here, and in this case on I node I can't apply, I'll have to apply on J node, but I'll just select this element. Okay, and activate. Okay, so the relevant elements have been activated. This is for ease of application of the loading. So we'll go to element, load case as breaking. Okay, load group doesn't matter because this we won't be activating in the construction stage. Okay, it is eccentric from the offset location in global Z direction. Eccentricity is 1.2 meter, right? So 1.2 meter above the deck. Okay, the acting direction is local X direction. Now when we say local X, that means the X direction of the element construction. Okay, if we view it in plan, it would be clearer. Okay, so say for the first element, the breaking load calculated, that is the left support, was 13.9 ton. So I'll just select this. Basically we want to apply concentrated force. Sorry, I'll have to do some re-input. This was for uniform force. So concentrated force, eccentricity in from offset global Z 1.2. Direction is local X. At x1 is equal to 0. So what is this x1? That you could notice from the guide diagram. The distance from the ith node, that is the first node. Okay, so this we are keeping it as 0 because we want to give the load at this location, right? So at x1 0, P1 I am giving 13.9 ton in local X direction. The load case is breaking, that's fine. Apply. Okay, so now we talk about this element. So the load in this case is 32.25 ton. So I'll just switch this to 32.25. Now the direction is local X. So as you can notice, it will come along the longitudinal direction of the element. Similarly for this element, it is 33.35. Apply. And for the final element, this has to be applied at the jth node. So relatively speaking, that is at x1 is equal to 1, that is n2. Okay, you see there are two options for here. One is relative, one is absolute. So if you want to enter the actual length of the member, say which is 2 meter, then you have to select absolute and enter 2 over here. Relative means this is the length ratio, your length considered divided by total length. So when my length considered and total length is same for the particular element, that means my x1 would be 1. Okay, that would be 2 by 2. Okay, so that is 1, and this P1 I am entering as 15 ton and apply. Okay, so as you can notice, for these elements it's applied at the ith node, and for this element it is applied on the jth node. Okay, so the breaking load is applied. Moving on, the uniform temperature loads will be applied now. So, yeah, by the way, you can notice the eccentricity here as well. The global Z eccentricity is 1.2 meters. So that's why the load is acting 1.2 meter above the deck. Okay, coming to the temperature. So go to temperature and pre-stress. Now we want to give uniform temperature right now. So in that case, these are the delta T values, that is uniform rise or uniform fall values. Okay, these are not the absolute values. So the system temperature that I have considered over here, it could be checked from structure, structure type, okay, and it's 0 degrees Celsius, right? So you just have to enter what would be the rise and what would be the fall. So we select the elements. Now these is also applied to the longitudinal elements only, and we'll go to load, element temperature load. Okay, initial temperature it will show over here as well. Load case is positive uniform temperature. Let us say the temperature rise that we are considering is 30 degrees. Apply. So that has been applied. Similarly, like before, we'll use the select previous option, and for the uniform temperature fall, we'll take it as -20, say for example, and apply. Okay, so 149 positive and negative uniform temperature loads have been applied. Similarly, the temperature gradient load. So for that, in this case, now we have defined, or rather the sections are taken up as PSC sections, right? So in that case, you could use this beam section temperature option, okay, with this PSC/composite option. So first of all, we'll add the positive temperature gradient. So we select that. As usual, load group is not there because this we are considering in post CS. Here too, the delta T values have to be entered. So the initial temperature is considered as 0, right? Now in accordance to IRC6, the positive temperature gradient is, at 17.8 degrees Celsius at the top, and over a length of about 0.4 meter, this will reduce to 0 in our case. And from the below, that is the lower side of the section, the temperature is 2.1 meter, which reduces to 0 in about 0.25 meter height. So we'll just apply that. We'll activate one more tree menu. Okay, let us just deactivate the temperature displays. Oh, sorry, values are coming now on display. Okay, this is done. Now we'll be adding the temperature gradient. So first of all, I'm adding the temperature for the top. So I'll just select the girder elements. I could either select in this way by selection by window, or in this case, since my material for the box is different, I could just come to workstation and double click on box. So all the relevant elements have been selected. Okay, reference from the top. B, that is the width to be considered. I don't want to enter that manually. I want the software to take it from section. H1, that is the distance from the reference line. So here we have taken reference as top. So I'll keep H1 as 0 and H2 as 0.15. Okay, so over initial 0.15 meter height, I want my temperature to reduce from 17.8 degrees Celsius to 4 degrees Celsius. Okay, so I do this input, I click add. Similarly for the second part, from 0.15 to 0.4, that is 0.25 meter overall height, I want it to reduce from 4 degrees Celsius to 0. Add. And now for the bottom part, so I am switching my reference to bottom. So H1 would be coming from bottom now. So this is 0. H2 is 0.25. Temperature from 2.1 degrees Celsius to 0. And I click add. Okay, so this is done. Now I have to click apply. So once I do that, my temperature gradient load is applied. As you can see, these yellow lines are coming up at the top and the bottom. Okay, so positive temperature gradient is done. Now the same thing would be done for the negative temperature gradient. So we go to beam section temperature, negative temperature gradient, PSC composite. Okay, section, and from the top we are starting. So first would be 0, then 0.25. Now these are delta T's, right, as I mentioned. So for negative temperature gradient, we have to enter negative values because our default temperature, that is the initial temperature, is 0 degrees Celsius. So temperature fall at the top is minus 10.6, and over the length of 0.25 meter, it rises to minus 0.7. Add. Then from 0.25 to 0.5, it goes from minus 0.7 to 0. Add. Similarly for the bottom part, I am just changing the reference to bottom. 0 to 0.25, it is coming minus 6.6 to minus 0.8, and for 0.25 to 0.5 for the bottom part, it rises from minus 0.8 to 0. Okay, we'll just select the previous elements and apply. Okay, so the negative temperature gradient load has also been applied, as you could see over here. Now finally the wind load. So as mentioned, wind load is going to be applied as pressure load for the line element. Okay, so under loads, static loads, element load. Okay, there is this option for uniform pressure as well as trapezoidal pressure. Now these are my element loads. Okay, so when we say pressure, so based on the direction which we are selecting for the load application, the software will automatically consider the area which is to be taken and it will apply the load in accordance to the area for the required section. Okay, so we are going to consider uniform pressure. Additional H from top, like we have assumed the crash barrier to be 1.5 meter in height. So besides the section height, we want to add that more 1.5 meter. So we have to just enter that value 1.5 over here. The application for the wind, we are considering, actually it can be two ways. We can consider the global y direction, okay, as well as for the critical case, if you want to check, you may even consider the local y direction. So you could select that, and the P value, that is the pressure value as shown in the presentation, it is taken as 1.653 kilonewton per meter. Okay, so we'll just select the longitudinal sections and okay, just check, yeah, the load case has to be wind and apply. So now when I look at the plan, the wind load is applied. Okay, actually there's been a mistake in braking load application. The calculations made were in ton, remember, but the braking load that are entered in kilonewtons, so that is not proper. So what we'll do is we'll use the table to sort it out. So we'll go right click on the table, we'll go to sorting dialog. By load case name I want it to be sorted, okay, and sort. So at the top all my braking loads will come. I am changing my unit to ton. So once I do that, my tables are also automatically updated, and as you can notice the braking load is way too low, so we need to change this. It is 13.9 ton, then 32.25 ton, 33.35 and 15. Okay, so now if I change the unit to kilonewton, okay, so these are the values which should have been applied earlier. Okay, so the braking load has been applied, rather modified. Now we'll go to the moving load definition. Okay, so for a straight bridge, usually what is done is we click on the first point, we click on the last point, and we are done. But for a curved bridge, that method will not work. For a curved bridge, we have to go for a different method, which is numbers. So to ease our input over there, what I'll do is I'll just select the box girder elements, and I'll just copy this node number. It's element numbers. It's 1 to 149. Okay. So now we'll go to the moving load application. So we'll go to moving load, select India, traffic line lane, add say A1. Okay, so class A first lane. Eccentricity, now this I'll have to it's 3.3 meters, right, as calculated in the presentation shown earlier. But eccentricity, now the one that I want to apply, I want the moving load on the outer side, that is the convex side, and not on the concave side. Okay, so for the outer side load application, the eccentricity has to be from right of the center. So as you can notice from the guide diagram, I have to enter a minus sign for the eccentricity in the positive y direction. So I'll enter minus 3.3 here. Impact factor I am considering as 0.088 in accordance to IRC. Okay, now see, this is what, when you say 2 points, this is what we usually do for straight elements. So go there and you click here. Okay, so this is the error that you will get, no beam element on the mentioned line, because it's a curve, so there won't be any line. So we have to go for picking. What picking will do is, it's for a long bridge, this is a cumbersome method. You have to click on the individual locations and it would be added, right? But for this longer bridge, it will be very cumbersome. So the next method is numbers. So I'll just enter 1 to 149 over here and I'll say add. Okay, so that's it. My class A lane has been first lane has been added. So I do that, I say apply. Similarly, A2 I'll be adding. So the eccentricity changes to 0.3. I'll just delete the existing ones and I'll click add again. Since I had clicked on apply, A1 was added, and now in the same dialog box I am applying for A2. I'll just click apply again. So as you can notice, my A2 load has also been added, and now 70R. So in this case, the eccentricity is minus 1.685 meter. The wheel spacing, that is the width of the vehicle, is 2.93 for 70R. Same impact factor. I'll just remove the earlier elements. I'll do add and OK. Okay, so the required lanes have been added. Okay, so we are considering the exterior side because that is going to be more critical. By the way, yeah, just as how the braking loads were added. Okay, I'll just show the braking loads again. Okay, so just as how the braking loads are added 1.2 meter above the deck at those specific element locations, in the same way centrifugal force can also be applied. The procedure is the same, so I'm not showing that over here. Okay, so centrifugal force could be applied in the same way. That would be one more different static case. So moving on, vehicle definition. Add standard, we are adding class A and class 70R. Okay, and the moving load cases. So class A moving load case, not auto live load combination. Add minimum loaded lane 1, maximum 2 for class A vehicle. We'll select both the lanes for class A and OK. Okay, so class A case has been added. Similarly, we'll add class 70R. Yeah, one lane would be loaded for if you're considering 70R. Okay, so the two required moving load cases have been generated. Okay, so the moving load definition is now done. Now what we are going to cover is the settlement part. Even the settlement application, at times it is not usually covered properly, is what we notice in our usual technical support. So today I'll show how settlement load could properly be applied. So we'll go to settlement. First of all, we have to create the settlement groups. Okay, so these are the nodes which are directly going to settle in accordance to the mentioned settlement value. Okay. Okay, these have to be nodes. Okay, and not just the support locations. So overall there are going to be 4 locations where supportment will directly happen, that is at left support, pier 1, pier 2 and the right support. Okay, So for the left support part, when I'm creating the settlement group, okay, so I just click on settlement group name is say left. I'm giving this settlement is minus 0.01, that is 10 mm, and these are the node list. Add. Okay, so as you notice, the top of the deck has also been taken up because that will also directly settle by as much amount. Okay, in case you are having a bearing or something wherein the bearing top would be settling by that much amount, you have to restrict this selection to the bearing top. Okay, so this is the left support. Similarly for peer 1, so I am giving the group name as peer 1, and now the node list. Okay, so I'll just go to plan for easier selection. Okay, so basically this node would be there from deck. So these are all the nodes which should be taken up for the peer settlement group. So peer 1. Similarly for peer 2. Okay, and finally the right support. Okay, so all the required support conditions, settlement groups have been created. Now the settlement load case. Okay, so load case we are giving name as set. Okay, we are considering all the groups. Now the minimum group that we want to settle is 1. That's when settlement will come into picture, and maximum number has to be restricted to number of groups minus 1. That is, in this case, since there are 4 groups, we are restricting it to 3. Now why we are restricting to 3? Because if you are saying say max is 4, so that means all the 4 supports are settled. So when we think about it, there is again no settlement effect which would be seen in the structure. Okay, so you do this, you say add. Okay, so the settlement group has been created, settlement has been applied. Now one of the important parts in basically our structural engineering, what it allows us to do is the superposition of the different static load cases, right? So there would be certain bending moment due to moving load, there would be certain bending moment due to dead load, and there is going to be certain different bending moment due to settlement. Okay, so if when we are giving the settlement, okay, so the other load cases, your moving load, your dead load, all of these also would be affected due to the moment redistribution happening due to the settlement. So what we have to do is we have to restrict this effect of settlement only to the settlement analysis and not take it to any other load case, because for all these load cases, when we are generating the load combination, at that time we are superposing these loads and we will get the effect. If we are not doing this, then what will happen is the boundary change, the settlement effect would be taken up for moving load, dead load, everything separately, and when you are doing combination, this effect would be multiplied in magnitudes. Okay, so to avoid that, we have to restrict this settlement of supports only to the settlement analysis. So for that, we have a feature which is boundary change assignment. So we go to boundary change assignment. Okay, we just select all. Now why I have done this is, what all supports are there in my model, I want all those boundary groups to be shown over here. So we will give a group name, says set group. We want the supports in this. Okay, add, and for the settlement analysis we have to change this to set. Okay, this is what the degrees of associated freedom associated with specified settlement would be assigned to that particular case only. Okay, and okay, so the boundary change assignment has been added. To verify, let us just check what the support group is. So support group includes all these locations, but the support of first and the second support, that is left and right support, is not included. So for that, we'll have to modify the boundary change assignment. We'll have to add all these three to the set group. So we can select all three and add the place. Okay, and okay. So the boundary change assignment has been done. Now for the moving load, if you remember, while defining the lanes, what I had done was I had provided the impact factor, right? So under moving load analysis control, okay, if instead of this impact factor you are going to provide say span length, so the software will automatically calculate the impact factor, but for that then you have to mention what type of bridge it is. So it should be IRC, and say for the calculation what output do you want. So for the plate elements, if at all you are using and you want the stress as well in the plate, which is usually required, so you have to activate this stress calculation. And for the frame elements, if you want to check the concurrent forces, so you have to activate normal plus concurrent forces and stresses. As well as if you want to calculate the stress due to moving load, you have to go for this combined stress calculation and click OK. Okay. Now what we will be doing is we'll be providing reinforcement for all my PSC sections. So for that we'll be using the PSC bridge wizard. So under structure, PSC bridge, for using this wizard, what you need to do first is you need to provide the span information. So we'll go to span information. Okay, say span 1, it's by selection. So what I'll do is I'll select the elements which are going to be there in the first span. Okay, I'll have to unselect existing things. I'll just activate the superstructure. Okay, so this is my span 1. I say add. Okay. Now I have to mention where the supports are. So it's at the I end of element number 1 and at the J end of element number 41. Sorry. Okay. And add. So span 1 is done. Now span 2. So to avoid confusion, let us just inactivate what has been done. So now the span 2 okay, so span 2 appropriate elements have been selected. We'll click add. At the support is at the I end of 42nd element and at the J end of the 103rd element. Okay, add. And the final one, span 3, similarly support assignments, add. Okay, and we are done. So we'll just close it. Okay, so the 3 spans have been assigned. Moving on now, the reinforcement application. So we'll go to section and reinforcement. Okay. What if you want to modify the section in certain ways, okay, then you could do that using the section tab. But for now, what we are concerned is the reinforcement application. Okay, so what I'll do is I'll just open the already existing input and I'll show you how it was done. Okay, so basically what we had done was we had defined the 3 spans, right? So first of all, we have to select for which span we want to give the reinforcement. So we select the appropriate span. Then what is the reference, that is starting point and the end point. So for my first span, starting point is support 1 and end point is support 2. That is the entire span. What I'm doing is I'm providing, sorry, this should be 16 mm dia bars, 64 number in longitudinal direction in top flange and the bottom of the box. Okay, so I just have to select the bar dia. I just have to enter the number over here. Area would be taken up automatically. What's my reference? That is, I am considering centroid. Y as 0. That is from center I am giving in both the directions. Z direction offset is 0.05. Right, the reference from top. So that is, my top cover is 50 mm and spacing considered is 150 mm between the longitudinal bars. Similarly for the bottom. Okay, so this is how you give reinforcements for one span, and if the reinforcement in the longitudinal direction is remaining same for the remaining spans, you could click on this copy current longitudinal information to other girders. Click on that, it will show you. You select the relevant spans and you click OK. Okay, so this was the longitudinal reinforcement. Then comes the shear reinforcement. Okay, so shear reinforcement also has to be entered in a similar fashion. The span you have to select your reference points, and what is the shear reinforcement that you want to give, what is the torsional reinforcement that you want to give. These have been calculated based on the reinforcement which you are going to provide for the entire section, and if we are going to consider the enclosed stirrup or not. So you just have to select this. Again, like before, you have to copy this information to the remaining girders and click OK. Yeah, so you'll get this particular error. See, whenever you are doing or executing certain function and you are getting an error, so just read the command message and it will clear that out. So what it says is the element is included in tapered section group. So you can't assign reinforcement to a tapered section group. So for that, what you need to do is you need to convert these tapered section groups into individual tapered sections. Okay, now manually defining such section should be quite cumbersome, but the software, when it has already defined the section and made the tapered group for us, all we need to do is we need to go to this tapered group, we need to select all, and we just need to click on convert to tapered section and OK. Okay, so overall there were these many elements, that is 104, which have to be converted into individual sections. So now that conversion is going on. Okay, once this conversion happens, the reinforcement could be assigned to each and every section. Now if you notice, earlier there were just 8 sections and now there are 112 sections. Okay, so that is done. You go to structure, PSC bridge, section and reinforcement, open. Okay, yeah, it's already there, the input that we have done, and OK. So once you do OK, 149 element data, 149 section and 149 reinforcements have been assigned. Okay, so if you want to check the reinforcement assigned, you could go to properties, you could click on any one section, just zoom in. Oh, sorry. Now when these reinforcement are assigned, basically the earlier sections are discarded and the new sections are created with the reinforcement. So what you could do is, if you want to remove the earlier sections, you just right click here, delete unused sections. Okay, so it's all gone. Now if I want to check the reinforcement, go to properties, I click on any one section and I just zoom in. So here are my reinforcement bars. Okay, in this case only the longitudinal reinforcement bars would be shown. The shear reinforcement bars are not shown in this particular dialog box. That can only be referred via the input which is made. Okay, that won't be visible over here. You can see it's something awkward. Okay, so this way reinforcement could be assigned for this kind of PSC section. Now all the load application that need to be done, all the reinforcement which need to be assigned have been assigned. Moving on, what we need to do is we need to perform the analysis on this model. However, since we are low on time, I won't be performing the analysis over here. Okay, but after the analysis is performed, I'll just show you briefly what inputs need to be made for the PSC design. Okay, so, or rather I'll just show you in the completed model once we have a look at the results. Okay, so this is the same model with, you know, completed boundary cases, boundaries and reinforcements and everything. One particular support condition which I forgot to show in the earlier models, that is this. Okay, so at the bottom of my pile I have considered those as end bearing piles, that is I have considered end bearing as well as friction, and so at the bottom I have only restrained the displacements, not the moments. Okay, so these are the support conditions which are provided for the piles. Okay, moving on, in the results, if you want to check, say if you want to check the deformed shape due to temperature gradient. Okay, so this is how the positive temperature gradient would be causing deformation, and these are highly exaggerated, so you don't worry about that. We consider this as real, so you could barely notice any deformation, right? But then it doesn't give an engineer an idea whether the behavior is proper or not. So these are highly exaggerated deformed shapes. Okay, similarly for SIDL, if we check, then it is like this. If we want to check the forces, the beam diagrams, so you could go to beam diagrams and apply. Okay, so now this undeformed shape will give you not proper idea, so we'll just switch it to proper undeformed shape. As you can notice, there is a kink over here. Now this kink is happening because the moment distribution is happening from your support, from your deck to your support, as this is a integral construction, so hence the kink. Okay, so this way you could check your forces, you could check your reactions, you could even go for your moving load tracer to know the vehicle position which is causing maximum reaction or maximum moment. Say for maximum moment due to class A, if you want to check for this element, say for example, if we write apply. Okay, so here it will give you the vehicle position which is causing the maximum bending moment at that location. So as you can notice, the vehicle is placed only in the mid span, because the vehicle placement in first span or the last span would have a relieving effect. So since we wanted to consider only the critical part for the mid section, the vehicle has been placed accordingly and this would be shown. Okay. Similarly, if you want to check the tendon losses, you could do that from simply the tendon loss graph over here. You could select whichever tendon you want and in which stage you want to check. Okay, so it will give you, okay, since these are bottom tendons, they will be activated at the end, so you will get the values in the last construction stage, because you could check for any number of tendons that you want, and all these outputs in form of result table could be obtained under the result tables. Okay, so now moving on, the PSC design input. What we have done is we have provided the reinforcement. Now we'll just select the relevant code over here, the parameters as to what all we want in output. We want all the ultimate limit state as well as the service limit state designs, right? So we'll consider that. Then the design material. So under PSC design, what we have done is we have provided FE415 reinforcement bar for all the different materials, though we need to give it only for box since that is the only PSC section. Then the design and output position. Now logically speaking, the design should be performed for the entire bridge, but the output has to be restricted to certain critical sections only. Now why is that? Design obviously we need to perform so that we could check what's happening at different locations, but output, if you are giving at all the locations, so what the software will do is if you want to generate the Excel report, it will give you the Excel report for all the 149 elements at the I and J location. So that would be 298 sheets, plus there will be result table sheets and all. So generating an Excel workbook with so many sheets will take very long time. Moreover, most of the system won't even have the capacity to open an Excel workbook which is having so many sheets, right? So to restrict that, what we do is we select certain critical sections for output. Okay, so in design position you go, and what you can do is you can select all your deck elements and you could just click on apply. So it would be taken for PSC design. And similarly for output position also, same input. Go to output position, sorry, not the same input. The critical sections need to be selected. So in this case it is 44 and 73, so you could do that. Then the load combinations. Okay, yes, so once the analysis is performed, you need to generate the load combinations for performing the design. So load combinations will be generated in the result, load combination, concrete design, and these are the load combinations which would be auto generated. Okay, so these load combinations are considered. Under PSC you have to select what load combination you want to design for. So you select all those and you perform the analysis, that is perform design. Once the design is performed, you just click on generate Excel report and you will end up with this kind of a Excel report. Okay, so what we had done was we had done what for 44 and 73. So we got Excel sheet with those element designs. Say if I want to show for an element, so as you can notice and shown in the PPT also, the clause numbers would be mentioned, the design considerations, factors as well as section properties, all of those would be mentioned. The positive moment check, okay, so how the neutral axis is being calculated, that would be shown. Okay, whether it is okay or whether it is failing, that would be shown. Where the particular input is taken from, the clause number would be shown, as you know. Okay, so yeah, it could be noticed that in this case my section is failing for negative moment, so it is shown as NG over here. Okay, similarly shear checks are done and shear it's fine. Okay, and even the crack width check is done. Logically it's not, you know, allowed. Of PSC, correct PSC sections are not allowed in IRC, but these are there in certain other international codes, and we do you know, take lots of guidance from certain other codes at times. So these options have been provided so that in case there is certain modification in our code in future, so that input could be considered. Moreover, if you notice that it's you know, crack analysis is performed and it's checked, so you could simply redesign these sections so that it's completely under compression. Okay, so this is the kind of report that you would get after performing the PSC design. Okay, now the new feature which has been added, the RC design. Because for that you go to design, and under RC design now IRC112 is available. Okay, so if you want to design a pier or a pile, then you could do that. Coming down to say let's do a simple pier design first. So design code is already selected. Concrete material we have given for pier and pile FE415. This is the same as what we did earlier for PSC. Now what we want to do is we want to check the section for design. So for pier, we just give what the cover is and what is the number of legs. In this case it's circular, so anyway we'll give 2. Okay, similarly for pile. Okay, so we have mentioned the cover and the reinforcement to be considered. Now say column section, we are going to perform the column design. There is no beam in this element which can be designed, that is RC beam. If I want to perform design of this pier, say for example, so I just select this pier under RC design, concrete code design, column design. Okay, so since I have selected one section only one section would be designed. Okay, so once this is designed, we can view it by member and we can view the design in graphic, whether it's failing. So what is the height is considered and what are the safety parameters, whether it is safe or not. Going by P by MU curve, where is the load exactly standing. Okay, and what is its safety in shear, it could be checked over here. We could even view the 3D PM curve. And if you want to view the detailed report, then you could just click on this detail and a text file with entire design considerations, what are the load cases that are taken up and what are the values which have been finally taken up for design, what formula have been used, whether it's slender or not. So all of those calculation could be accessed from this detail. Okay, now these are temporary files. So if you want to save it, you click yes, or you click no to destroy it. Okay, so that is your simple pier design. Now coming to pile design. Okay, so piles are actually divided into 1 meter segment length over here, right? But overall length of the pile is 30 meter. What we want to do is we want to design for that, say for example. So what we have to do is we have to go for member assignment. Okay, so basically what is member assignment? Member assignment means though there are several elements, that is if we check one pile, okay, there are 30 elements in all like this, but if I want to consider this as one element for design, then I have to use this member assignment option under common parameter member assignment. Now what I have done is I have already done member assignment for one side of the pile cap and I have not done that assignment for the left side. So I'll show you what is the difference in that case. Okay, so say we have selected one member over here. I'll rather select only one member. Okay, say I have selected one member over here and I am selecting one member over here. Okay, now if I go to RC design, concrete code design, column design. Okay, so what will happen is for the left side, that is P1, the analysis and the design would be performed only for one element of pile. Okay, I'll just view this by member to make it more clear. Okay, let us say we are considering this 202, so I'll just check that graphic. Okay, so see the column height which is considered over here is 1 meter and the factor of safety and all seem to be quite high, 0.7. Okay, shear it's no need to be checked. Okay, however when I check for element 203, that is on the P2, and I go to graphic, the length considered is 30 meter and look at the acting and the resisting forces. So it is just safe. One means maximum utility and it is utilized up to almost 95-96%. Shear is still not an issue. Yeah, it's about 25% only. Okay, so this basically is designed for the entire 30 meter length of the pile and not just 1 meter short thing. That would give you a wrong idea. If you are performing design for a long section, a long element which is made of several small elements, then first of all you need to go for member assignment and you need to perform the design. Okay, so this is how you go about it. The session has gone a bit longer than expected. Anyway, so if you have any questions for us, just let us know. I'll try to answer as much as possible right now, or you could get back to us on as most of you do many a times, techsupport@midasit.com. So kindly let us know of your review of the webinar as well as any questions on tech support at Midas IT. Okay, thank you.